you get it? Okay, I'll begin. Dear Father, we thank you for this day. I thank you for these students, most of them. Just pray be with us today. Help us to glorify you, what we do, Lord. In your name I pray. Amen. Let's see here. So, yeah, most of you I like. Let's see here. Just kidding. All right, so today we're going to talk about the problem of nth order differential equations. Okay, so we've been studying first order differential equations, which are, like they sound, equations that only involve the first derivative, for the most part anyway. Now we're going to study so-called nth order linear differential equations. Here's what it looks like. Definition. If there are functions, let's say a naught, a1, an of t for some t which is some interval of the reals. Usually, more often than not, the interval is the whole real lines, but sometimes we look at like half interval, like half the just positive time or something like that. Oh, in fact, do I want to stick with t? I'm going to change that to x. I'm going to use x as my independent variable if you don't mind. Okay, then basically what we're going to look at is something like an, the nth derivative operator. Fine, let me write it this way. The nth derivative of x, all right, plus an minus 1, the n minus 1th derivative, all right, and so forth and so on. Eventually we get to a sub, say a sub 2, y prime prime of x, plus a1, y prime of x, plus a naught times y. Again, it's a function of x, fine, you got me. And all of that's equal to, let's say, I don't know, f of x there. Okay. So this is what a nth order, this thing right here, I'll put a box around it, this guy, this is a nth order linear ordinary differential equation, ODE, right? In independent variable what? X, and dependent variable is y. So our goal, right, our mission, should you choose to accept it, you will choose to accept it, is that we find y as a function of x, subject to this condition, right? Now sometimes we'll add initial data, right? We might add that we also know the value of the function, the value of the dependent variable, its derivative, its second derivative, and so forth, all the way up to its n minus 1th derivative at a particular value. That would give us what's called an initial value problem. We'll get back to those in due time. So let's see here. Other terminology you should know about. If f of x is identically equal to 0 for all x and I, then star, they call this thing star? Let me call it star. Then star is homogeneous. Okay? It's a homogeneous differential equation. So the main technology we're going to develop in here to understand this problem and rip it apart piece by piece is what's known as, well, I suppose it's the calculus of operators. We're going to use operator notation, that much I can say for sure. So let's just, as a starting sort of foray into that world, let's rewrite our given differential equation as an operator equation. So, here's a definition for you. If I'm going to use d for the derivative, all right? So d is going to be equal to d dx. So like d squared is going to be d squared dx squared, and so forth. The nth power of d is the nth derivative with respect to the the variable. So, for example, what this means, like notation-wise, is if I have d of y, this is equal to y prime, right? Or, and so forth, if I have the nth, d to the n acting on y, what that means is the nth derivative of y with respect to x. Okay? So this is the operator notation. So in particular, I'm looking at the differentiation operator, all right? So that's a starting thing. And then the other thing is I have like another notation. Let's see here. Well, let me not belabor that. Let me just use it, and you can see it. I don't need to really define it. I just need to use it. You'll know what I mean when I write it. So this can be rewritten as the following operator equation. This is an times d to the n plus an minus 1 y to the n minus, not y, no y, d to the n minus 1 plus dot 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 plus a2d squared plus a1d plus a naught. And then we put some square brackets like this to emphasize, well, actually, I don't need that. I take it back. Put ordinary parentheses like this. And then sometimes I'll put square brackets here to emphasize it's an operator and it's acting on a function. An operator is something that takes an input of a function and its output is another function. This is really not new. Calculus 1, we teach you in the operator is d dx, right? You differentiate a function, you get out a function. Function in, function out, operator. So this operator takes in y, and what's it do? It spits out f, right? You notice I'm omitting the x dependence there. I could put back in the x dependence. I'd have to put like a(n) of x, a sub n minus. Anyway, the writing of x gets really old. You see, this even is a cheat, right? Because really I should do of x, of x. See how annoying that is? Of x, of x, of x. As you see, I didn't even have the patience to write it to start with. But technically, those are all, could be functions of x. All right, so let's give this thing a name. And I'll try to just show you why this is such a useful compact notation. We call this thing L, all right? So definition, T is a linear operator. What's that mean? So for us, it just means this. T of like C1, Y1 plus C2, Y2 plus da 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 plus Cn, Yn is equal to, well, C1 T of Y1 plus C2 T of Y2 plus da 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 plus Cn T of Yn. In other words, a linear operator is one where you can pull scalars out and you can break up additions. Do you know any linear operators? Limits? Yeah, limits are like linear operators. Integrals. The derivative, right? The second derivative, the third derivative, the fourth derivative, the 15th derivative. Laplace transforms? Wait a minute, no, we don't know what those are. All right, so anyway, there's lots and lots of linear operators. In particular, I would make the observation, so here's an observation for you. L is a linear operator. This L. Because it's formed by adding together linear operators and multiplying by scalar functions. I mean, you could just feed this thing a sum of functions and see that it works if you like. But I'm just going to make that observation. And so I have a little theorem, right, that we can state without a lot of work. If, and I'll just do it for, well, let me do it for more than, I guess if I do it for 2, you guys will understand it for more. If we have L of y1 equals to 0, and if we have L of y2 equals to 0, all right? Oh, fine, I'll be greedy. Suppose you got, how many of them? Suppose you got like k of them. So suppose we have k. These are called homogeneous solutions. What is that? What can we do with those? Set them equal to each other. I guess you could say L of y1 equals L of y2. That's true. But what I was fishing for is that we could do this. L of c1y1 plus c2y2 plus plus like ck yk, where c1 through ck are constants, right? Since L is a linear operator, I can pull the constant out, right? I'm getting to where you guys are trying to get me to go. I'll get there eventually. Plus plus ck, L of yk, right? So I can pull the constants out. But then we're assuming that these are homogeneous solutions, which means what? Which means that those are 0 plus 0 plus 0 plus 0 plus 0. By assumption, this is 0, right? And so, in totality, 0, right? So what this says, I'll put it in words, is the linear combination of homogeneous solutions to L of y equals to f is once more a homogeneous solution to L of y equals to f. So what is it, before I get too carried away, and we're about to look at specific examples and build a machine to solve many, many problems, okay? But we need a little bit of backdrop here before we get into that. What does it mean for something to be a solution to the star over here? What does that mean? When is y a solution to star? What happens? You plug y in to the differential operator L. What comes back out? We have to get back this function f. All right? So if f is non-zero, right, is a homogeneous solution a solution? If L of y is equal to f, and that's not equal to 0, then L of, say, y1, whatever, let's say L of yh equals to 0, means that yh is what? Is not a solution to the problem. Let me give this thing a name. Let me keep calling it star, okay? Because it gives you back 0. It doesn't give you back this non-zero. This f here is called the forcing function as a point of terminology, forcing function. It's also called the inhomogeneous term. But I like forcing function. It reminds me of physics. You're like, well, if it's not the solution, and our main order of business in here is to find solutions, then who cares? Well, let me tell you the big story. So, long story short, what we're going to learn here is to solve the non-homogeneous problem, we have to find all the homogeneous solutions for the problem, find one particular solution to the problem. You put those together, that gives you the general solution, which is what we're after. So that's a theorem. Theorem solution to L of y equals to f has form y equals to c1 y1 plus c2 y2 plus da 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 plus cn yn plus yp, where y, well, let's say L of yi is equal to 0 for I equal to 1, 2, da 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 n. So this is, I'm jumping ahead a little bit, but I think it's useful to have the big picture early on so you know what we're doing, why we're doing what we're doing. Ultimately, we want to solve the non-homogeneous problem. It takes a little bit build up to get there. But ultimately, the solution to the non-homogeneous problem, it's going to be built with two things. It's going to be built with these homogeneous solutions, and then this what's called particular solution. Here, L of yp, it's really a specific solution, and it gives you back f. Now, so I'm not really going to say anything else more about this. This is another day, all right? So we're totally focused today on how to find homogeneous solutions to differential equations. That's our first order of business. But I'm telling you, once we do that, that's going to be an integral part of forming the whole solution to the problem, right? And that's how you do it. Okay, so I've shown you some basic theorems. Sum of homogeneous solutions is, again, a homogeneous solution. This is our basic terminology. And so at this point, I'm going to make a, well, at this point, I think I need to start developing theorems about operators. So let's get to that. So here's another definition for you. If T and S are operators, then here's how we define T times S is understood to be composition of T and S. So like T times S of Y is, what that means is a T of S of Y. So multiplication of operators is composition of operators. For example, I mean, I already used this. Like, for example, what would T squared acting on Y would mean T of Y, right? So I already used this notation for the differentiation operator, but I'm saying it's also true for other operators. Okay? Other things, kind of more mundane, here's sort of a mundacity. If I have an operator plus another operator, how's that defined? Right, we take Tx and Y plus T plus S acting on Y. So that's how we add operators. What else should I define? What if we have a constant times an operator? How's that defined? Yeah, we pull the, exactly, it's just the constant times the operator acting on Y, right? Now, there's another kind of a little bit subtle thing. A number serves as an operator. So here's an odd thing. Like 3 is an operator. What do I mean? Via multiplication. So what I mean by that is just, if I take 3, right, it's really stupid, and it acts on Y, that's just equal to 3 times Y. Okay. Here, let me make it look like it's more than that. So 3 acting on Y gives me a function. It's a function of X. That's equal to 3 times Y of X. There, it looks like I said more now. There I'm writing the dependence of the new function on X explicitly. Remember, an operator takes a function to a function. To define a function, we have to define its value on its domain, right? What it does to X. Okay, so we got addition, we got composition, we got multiplication. I think we're good to go. Let's try to do something a little bit more interesting. So theorem, let me call it proposition 1 actually. Prop 1. If I have d plus alpha times d plus beta, I get to d squared plus alpha plus beta times d plus alpha beta. So here I'm saying alpha and beta are constants, but that's a very good question. Numbers. All right. All right, so the way we prove an operator equation, yep.
Is the d going back to the derivative?
Yeah, d is always going to be differentiation today. And well, the rest of the course. Yeah, if you're like, I'm going to make my domain d, I'd be like, no, you're not. I might do that at some point. If I do, you should remind me that that's wrong. Yeah, d is reserved notation here. It's for differentiation. So d alpha, d plus beta, that acts on y. How's that work? By definition, this is what? This is d plus alpha, that operator, right? Acting on d plus beta, acting on y. I'm not insisting that you have to write all these steps if we have a test or something. I'm just trying to communicate to you the logic at the moment, so do not despair. It's not like I'm going to be like, prove this by limit laws on the next test or something. I mean, that's not what this is about, okay? I'm just trying to explain to you the substructure here. So d plus alpha, and then how's this work? Well, that's what? That's, let me use the prime notation if you guys don't mind. That's y prime plus beta times y, okay? Where y prime is, of course, dy dx. Then, by definition, this is d of y prime plus beta y plus alpha times y prime plus beta y. And here is an instance of that weird, odd thing, alpha is an operator. So alpha multiplying the thing just multiplies the thing. I mean, so this gives me, I'm going to write over here, this gives me y prime prime plus, I can pull the, beta is a constant, right? It pulls outside the derivative. So I get beta y prime plus alpha y prime plus alpha beta y. But if you tilt your head and squint, you can see that that's exactly d squared plus alpha plus beta times d plus alpha beta acting on y. I don't know if you ever thought about this before, but this is kind of surprising. Right? It says that derivatives and multiplication by number obey the same polynomial algebra as polynomials. Right? I mean, corollary. This is, I mean, here. Let me put the corollary up here to save us some writing. Can you switch the roles of beta and alpha here? I think you can. This is just addition of numbers, multiplication of numbers, commutative, right? So this is equal to d plus beta times d plus alpha, right? We can commute. We can commute linear factors of the derivative and multiplication by constant. That's huge. What that means is we can manipulate polynomials in the differentiation operator and multiplication by constant just like we do manipulate polynomials, right? Like we could factor a differential operator, for example. All right, before I get back to that, I want to help impress on you how special that proposition is in the world of other operators. So it's helpful for us to look at an operator which is not like those. An operator which is built of ugly things. Well, not too ugly. Here, let me just, I think if I do this example, it'll help bring it to life for you. So let's look at, ooh, this is an ancient marker. I wonder if this works. Sort of. Let's look at t equals to x squared d squared. Oh, that's not what I want. I want to look at t is equal to x times d. Right? And I want to compare that to t squared and see what the difference is in these operators. D still means differentiation with respect to x. But this, what's this mean? So I haven't really defined this yet, right? But let me show you what that means. This, I mean, I haven't defined it yet, but I already used it in what I just erased as a point of notation. You know, like, for example, sidebar, we could have the differential equation y prime prime times x squared plus xy prime plus 3y equals to, I don't know, hyperbolic sinh of the inverse tangent of x. I mean, you know, whatever. This would be x squared d squared plus xd plus 3 acting on y equals to, well, that thing. I mean, let me give it a name. It seems like Pac-Man, appropriate name. So that would be Pac-Man. So I'm using like this multiplication of function times the operator notation. It's pretty natural, you know. So I'm using that here. So what this means specifically is t of y, right, is equal to, let me be really pedantic about it for just a second. I hate to do this, but I'll do it. So if I write in the x dependence, this is equal to x times, you know, d of y. Well, I guess it's better to write this as dy dx. That's, but you know, I'd rather kind of write this, I'll write it like this instead. So this is t of y would be equal to x times dy. So the differentiation's acting on y, and then we multiply by x is what it is. So what do you guys think? Is t squared, is this equal to, question mark, is it equal to x squared d squared, right? I mean, if this operator was so nice and friendly, like this one over here, like you didn't prove anything. Like this is just obvious, right? Like of course d plus alpha times d plus beta is d squared plus alpha plus beta times d plus alpha beta, right? I mean, it just makes sense. I mean, like that just makes sense too, right? Like that should be what it is, but yet it is not the case. Let me show you why. In fact, this is incorrect. Because you can't take the square root of a derivative. Well, I don't know. There are many ways to skin a cat, I suppose. The important thing is that at the end of it, the cat's dead. But, oh, I'm sorry, cat lovers. Let's see here, t of what? Ty is what? X. I'll write y prime because that's a nice notation. But remember that t is what? This t, if you allow me to erase this and rewrite, this is actually x times the differentiation operator, right? Acting on x times y prime. I like to use some healthy mix of d dx, and the big D, and the y prime as to confuse the students. But keep in mind that I'm used to using three notations for the same thing, namely d of y is equal to dy dx is equal to y prime. These are all just notations I find convenient depending on the emphasis I'm making. Anyway, my point to you guys, this is a product. So we got to do the product rule, right? So here, you're looking at, you got yourself an x, and then you got a y prime, right? And then plus x y prime prime. So to go back to the operator notation, this is x d plus x times x, which is x squared, d squared, acting on y. So one of the reasons I like to show you guys this example is it emphasizes something which maybe you don't appreciate yet, but to derive an equation for operator, to derive a so-called operator equation, what you have to do is you have to show that the two operators are equal for all possible inputs. You see, this guy right here is equal to this guy over here for all possible y's. That makes sense, right? We have to look at twice differentiable functions, you know. Well, if the math majors haven't asked yet already, I'm probably safe. There are plural math majors in here, though. Is that correct? Figured. Okay, yeah, that's two. Okay, that's good. Good. Many times I'd have to be singular, or you guys are the empty set. I can say that because you're here. Let's see here. Sorry, engineers, but you guys tend to not care as much about stuff like empty sets, which is fine. It does seem kind of vacuous. So t squared is equal to, as apparently, what is xt? It's t again, isn't it? And what's this? Well, this is something that has no name, right? This is the thing that need not be named. I'm just calling it x squared d squared. So there you go. That's so it's not the case that t squared is x squared d squared. There's also this thing. So the naive algebra doesn't work when you have operators that don't have constant coefficients. This is a non-constant coefficient, right? So the functions I wrote in the equation at the start, those are called the coefficients of the differential equation. The a0, a1, a2, da da da, an. These are the coefficients of the differential equation. Apparently, there's something really special about the case that all of those coefficients are constants. See, if all of those coefficients are constants, that means that we have this technology to use, which is huge, right? So I can actually solve problems like I was doing over here, like this one I wrote up here, modulo the monstrosity of Pac-Man. So setting aside this is a pretty well-known problem. It's called the Cauchy-Euler problem. We'll see how to solve that. That's not that bad, actually. These can be tamed. These equations, you notice this equation says what? It says x squared d squared. It's not great, but you know what it is? It's still a polynomial in t, isn't it? See, x squared d squared is still t squared minus t. So yeah, that naive thing doesn't work, but I can still take x squared d squared and I can rewrite it as a polynomial in the operator x times d. It turns out that'll be all I need to generalize what I'm about to do to this problem, but now I'm getting ahead of the story. So let's look at the constant coefficient case, because that's really where it's at. So I'm going to build here for the next about 20 minutes or so a machine which allows us to solve any constant coefficient nth order differential equation. Let's do it. What we're about to develop is so simple that even though I'm how long into class? Oh man, well I still got what? 39 plus 3, 42 minutes. That should be plenty to do a bunch of examples today and build the machine if I'm just careful. All right, so we're going to build a series of lemmas. Lemma 1. So I forgot to, I said it in words, but let me just emphasize again. We're working towards solution of L of y equals to 0 in the case L is equal to an d to the n plus da 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 plus a2d squared plus a1d plus a naught, and this is the huge condition, a naught, a1, it means bigly, it's a bigly condition, a2, da da da, a sub n are constants. And I'll tell you what, I'll make them real constants. This is what we're trying to solve right now. Okay? So, you know, we know how to factor polynomials, right? So if you think about it, we're going to be able to factor this into something like an times d minus lambda 1 times d minus lambda 2 dot 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 times d minus lambda n, right? This can be done by the fundamental theorem of algebra. And what? Well, by the fundamental theorem of algebra and repeated applications of that proposition 1, we can factor the operator like this, all right? Okay, so let me develop some lemmas, and I'll come back to this idea. Lemma 1. All right, here we go. If we look at d minus lambda times y equals to 0, right, has solution y equals to e to the lambda x. Okay. Proof. Oh. All right, hold on. This is tricky. So we plug in e to the lambda x, what do we get? The derivative of e to the lambda x from the first term, right? Minus lambda e to the lambda x on the second term. What's the derivative of e to the lambda x? Well, chain rule, right? So this is lambda e to the lambda x minus lambda e to the lambda x. 0. Yay. Yeah. Now, if you're like, I would like for you to derive this, sir. The fact that you can pull it from the thin sky doesn't impress me. Well, fine. I hear you. I feel your pain. This, in other notation, is dy dx equals to lambda y, right? Separate variables. And integrate both sides. We get natural log absolute value of y equals to lambda x, exponentiate both plus constant, exponentiate both sides, we get y is equal to some constant times e to the lambda x. Separate, integrate. But I don't care about the k, I just want to find a solution. Eventually I'm going back to that theorem I wrote there. And I just need particular homogeneous solutions. I don't need like arbitrary multiples of them, because I'm going to put back in the arbitrary multiple in the theorem later, like the C1 through Cn I wrote. So I don't need this constant. So I just set the constant equal to 1 for the sake of bookkeeping. But I mean, fair enough. I could put a 3 here, it would still be true, right? Like, I don't really care about it, but I could just as well put a k here, and it would still be true. All I'm really interested in is k equals to 1, so I'm just being minimalistic, but it is true we can get a little bit more. I mean, but that's all I want. So you can derive it if you want, but I'm going to stop deriving things and just show you why things are true for a while. So this we could have already done, right? You guys know this. This is not. So what's next? Well, how about this? Lemma 2. Lemma 2. D minus lambda squared, acting on y, equals to 0, has solutions. y1, I should have called this y1. y1 equals to e to the lambda x, and y2 equal to x e to the lambda x. All right. So let's look at the proof of this. The first part's kind of easy. So if I look at d minus lambda squared, acting on, e to the lambda x, what happens? That's d minus lambda acting on d minus lambda e to the lambda x. But what did we just get done showing about d minus lambda acting on e to the lambda x? I mean, we just proved what? See right here? we showed that this gives me back 0, right? So what is this? This whole shebang here is exactly 0, right? One of the things I should have told you guys about linear operators, but you kind of already know, what does a linear operator do to 0? What? What is it? It does something to 0. It's just kind of boring. Differentiate 0, what do you get back? Integrate 0, what do you get back? So it's a constant. Gotcha. It depends what kind of integration we're talking about. But yes, linear operators send 0 to 0. So d minus lambda is a linear operator. Okay. I guess I haven't proved that, but you could easily prove that. But d minus lambda isn't a linear operator. And so when you feed it 0, I mean, it's easy enough to think through. What happens when you plug in 0 to this? Lambda times 0 is 0. Differentiate 0, 0. So this, of course, is 0. So in other words, the solution we already had in lemma 1, still solution in lemma 2. And what's the more interesting part? X, right? So what happens when we look at d minus lambda squared acting on x e to the lambda x? So that's d minus lambda times, well, d dx of x e to the lambda x, right? Minus lambda x e to the lambda x. So I just applied the first copy of d minus lambda to the function, and then what happens? Product rule, right? So we get a product rule here, which gives us a e to the lambda x, and then the second term in the product rule gives me plus x times lambda e to the lambda x, but then I've got minus lambda x e to lambda x still left over. So you see what happens with the lambda x e to the lambda x terms. What happens to those? They cancel, right? See that? So this guy and this guy, they cancel. And we're left with this guy again. But we already know what happens to him when he hits d minus lambda, right? What happens? 0, right? So there you go. That proves that x e to the lambda x is a solution of d minus lambda squared acting on y. Right? Yes, sir.
Is this thing going to apply up to y sub n?
So Zach wants me to generalize. I hear you, Zach. I'm gonna bite. Lemma. Maybe we should call this lemma n. I'll call it 3 though, which is if we look at d minus lambda to the n acting on y equal to 0, this has solutions y1 equal to e to the lambda x, y2 equal x e to the lambda x, and so forth and so on, until I get to what's the nth one, Zach? I'll do the easy part, e to the lambda x. X to what power?
N minus 1.
N minus 1, right? So if you want me to give you a proof, some of you do, some of you don't, I'll give you a proof by induction. Assume true for some n in, the natural number is greater than or equal to 1, and then consider d minus lambda to the n plus 1. So if that acts on x to the n, e to the lambda x, what do you get? Sorry, as soon as I write this down, I regret writing it. You win. Let's see here, e to the lambda x. So I'm trying to look at the most interesting function in the n plus 1 case would be the x to the n e to the lambda x. All of the lower functions still automatically 0 by the induction hypothesis. And then basically it's the same calculation we've already done. Like this gives me n x to the n minus 1 e to the lambda x minus x to the n, lambda e to lambda x, and then that's a plus, and then minus lambda x to the n, e to lambda x. And so like those terms cancel, right? And what are you left with? Cancel. And this goes to 0 by the induction hypothesis. Don't worry, guys. I'm not planning to ask you guys to do induction proofs on tests or anything. It's just, I'm sorry, there's still a little bit of a mathematician left in me today, and it's making me do this. I'm sorry. The point is, you keep doing this calculation. It just keeps going and going and going and happening at every level. Just for the next order, you just add x times one more x at each order. So like, here, let me make up for the badness of the last minute in this lecture by giving you an example. John. All right, who is that? Is that right? Okay, I hear something. I hear something. Example. If I was studying d minus 3 to the 4th power times y equal to 0, right? I can write down solutions to this. Solutions of y equals to e to the 3x, y2 equals to x e to the 3x, y3 equals to x squared e to the 3x, y4 equal to x cubed e to the 3x. Solutions! Woo! And yeah, those are the 4 solutions to this 4th order differential equation. And by theory, I haven't told you yet, if you take a linear combination of those, that's the general solution. That's messed up. That was very little work on my part to solve a 4th order differential equation. Consider how much work you've had to do to solve a 1st order differential equation. Anyway, so there's an example. All right, so there is some fine print here, isn't there? What is the thing I've been skirting so far? I said alpha and beta were numbers, didn't I? Right? What kind of numbers? One is real, one is not. Very good. But if you look at these lemmas, right? And you go back to the last class, the thing I didn't prove, but it would be easy to prove using the things we looked at last class. In fact, this calculation still makes sense when lambda is a complex number. The derivative of e to the lambda x is still lambda e to lambda x when lambda is complex. So all of the steps I just made in these lemmas are legitimate, even in the case that lambda is complex. But what's the rub? The rub is, let me show you an example before I prove the theorem. Not much of a theorem really to prove. But for example, if we have d squared, let's say d squared plus 4 acting on y equal to 0, right? Well, this thing factors into d plus 2i, d minus 2i, right? So if I just focus my attention on, say, d minus 2i, what's d minus 2i, y equals to 0 by my lemma 1 says what? What do we say our solution is? Y equals to what? Not minus 2i. I chose the minus because I wanted to get rid of the minus. Yeah, 2ix. Now, remember, by Euler's formula, this is the cosine of 2x, right, plus I times the sine of 2x. So, in other words, the real part of e to the 2ix is cosine 2x. The imaginary part of e to the 2ix is sine 2x. So lemma 1 actually has hidden in it sines and cosines in the case that the lambda is complex. Now, our real goal I did this on purpose, okay? These are real coefficients. And in fact, let me tell you, I said solution, right? But if you want me to really be more clear about that, is what I want is we want the real valued solution, right? We want the real valued solution. And so we need to find n real functions to form that solution from. So like here, you're like, wait a minute, how can that make sense? Because if it's a complex thing, it gives me two complex factors, right? And even one complex factor gives me two real solutions. So wouldn't that say that I get 4 solutions to each complex thing? But what happens when we look at the conjugate root? What are the solutions that stem from like d plus 2i? Lemma 1 tells me what this time? E to the minus 2ix, right? Which is cosine of 2x minus I times the sine of 2x.
By that, I sine 2x cancel.
Oh, you're thinking about adding it? Yeah, fine, but let me standpoint here. So the real part of e to the minus 2ix is what? It's still cosine of 2x. What's the imaginary part? Minus the sine of 2x, right? So do we really have any genuinely new functions? No, not really. We're still just getting sine and cosine. We already got those. Those are boring. I mean, what I'm trying to tell you is, like, if you've got 2i, it's easy. If you've got, let's say you've got 2i as a friend, you don't need minus 2i. It's got no new stuff, right? So, like, you don't need like conjugate friends. Just take one of them. You don't want the conjugate. Like you've already got all you need with the one friend. Don't also make friends with the conjugate. Yeah, sorry.
Since minus sine of 2x is kind of different.
Oh, well, it is a different function in the sense of like its graph is different. But as far as the differential equation is concerned, it's not different. Ultimately, we do something like y equals da 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 plus say c, I don't know, c whatever, c10 sine x, right? Your solution would be like da 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 plus c, pick a favorite number, I don't know, 42 minus sine x. So both of these terms in the general solution, they allow for the same set of possibilities because we can just make the constant different in front of them. So the fact that we're eventually adding a constant, we're adding linear combinations of the things we're finding, makes when they're just multiples of one another not different or interesting. Yeah. Fun fact. If L of z is equal to f plus ig and z is equal to, say, the real part of z plus I times the imaginary part of z, then what? So I'm assuming L is a real differential operator, okay? So suppose L is a real differential operator. If L is a real differential operator and we have a complex solution, all right, then what that means is something very cool. And actually, oh man, I don't need all this. I need to be lazier. What did I say? Homogeneous. No f plus ig. That would require thinking. 0. 0. So look at this. So we have L of the real part of z plus I times the imaginary part of z equal to what? L of the real part of z, we can pull the I out, L times the imaginary part of z, right? This is all supposed to be equal to 0 if you allow me this small manga style calculation. So I can have 0 equals to this only what? So, I mean, this is real. This is real, keeping it real. Sorry, too many puns. The point is, if I have 0 equals to this linear combination of a real function plus I times another real function, it forces what? Exactly, it forces both of them to 0. So this has to be 0, and that has to be 0. That's the theorem I'm trying to state. Then both the real part and the imaginary part are 0. The relevance here is that you didn't even notice it, right? But I was showing you the real part and the imaginary part of like e to the 2ix. If you think about it, you might have been like, well, who cares? You don't know that those are solutions, so what's the relevance? Well, this is the relevance. The real part and the imaginary part of a complex solution to a homogeneous real differential equation are themselves solutions to the differential equation. So in the case that we have a complex factor in the polynomial, what we do, we find the complex solution, right? And then we just pick off the real part and the imaginary part. Those give us two separate solutions to the problem. So I think I have shown you enough that I can actually do some examples. We're covering chapters 4 and 6 of your book, if you're looking at the book. But my notes do chapters 4 and 6. Chapter 4 is the second order problem. Chapter 6 is the nth order problem. I like to look at them both at the same time because if I build the theory right, we can do everything at once and not reinvent the wheel, right? Yeah, we have more time to do Laplace transforms and other things later. So, some examples. And I'll be using a theorem that I have not stated carefully yet, but it won't bother you. Example 1, if I'm going to solve y prime prime plus 3y prime plus 2y equals to 0, so I want to solve this. All right, so here's what I do. I convert it to operator notation. I factor said operator. There's one other idea I haven't shared with you guys yet, and I'll share it with you here in a second once we catch our breath. So, by lemma 1, what's my solution from this? From lemma 1, my solution from this? From the theorem, which I have not stated carefully yet, but I'll show you an application of it. The general solution is y equals to c1 e to the minus x plus c2 e to the minus 2x. There you go. That is the general solution to this problem. There's something that should bother you if you're really trying to follow me here. How is it that I know which one to do first? I mean, how do I know that? I know that e to the minus x solves d plus 1, right? But what does the d plus 2 do to it, you know? So let's look at that for just a second here. Little theorem that I think is important to state. If you have L is equal to L1, L2, say Ln. So this is factorization. So we've factored L into n-fold linear operators. So in other words, I'm saying we've taken the differential operator and we factored it into, and it doesn't have to be n, it could be less than n, it could be k of them, fine, k. All right. There's nothing, I'm not saying it has to be the same as the order of the problem, is my point. If then, if there is some